I first of all want to find out just how many of you took Physics 105 either from me or from Dr. Benyon. Raise your hand. Okay, that's a lot of you. More importantly, how many of you did not take it from me or from Dr. Okay, okay, keep your hands up, people. Look around. If there's someone with their hands up, that's your new best friend. You've got to take them to lunch and explain to them how the class works, okay? Because they're new. They don't know. How many of you had tutorials that were in person where you actually went to the, okay, so you took it a while ago. We'll talk about that in a moment here. I want to just point out that Physics 105 is kind of boring. I mean, we're talking about blocks sliding down an inclined plane, right? With friction, without friction. That's as exciting as it got. In Physics 106, that's where all the good stuff happens. That's where we talk about the really exciting topics. And if I had my druthers, I'd just teach 106 all year long. That'd be so much more enjoyable for me. So you're in for some good times. As far as the break is concerned, I went to Orlando and I took all of my kids and their spouses and our grandchildren, 27 of us in all. I'll be paying for it the rest of the year. But going through It's a Small World After All with a 2-year-old granddaughter was just magical. I mean, she was just so excited. And then to take these two yahoos on, I still call it Splash Mountain, while all the fireworks were going off, it was just amazing. So we had a good time. Before we go any further, would someone, Friendly, would you be willing to give us an opening prayer? Blessing on your head.
I can just be loud. Can I just be loud? Okay, I'll take this. Dear God, we're very grateful that we can come here to Chem 106 with a phenomenal teacher, and that, or not Chem 106, Physics 106. Please bless us that we can have the presence of mind and the concentration to be able to really dive deep into this subject and understand it fully. And we thank you for all that you've done for us in our lives so far, and for BYU, such a phenomenal place. And we say these things in the name of Jesus Christ. Amen.
Thank you, Brinley. Okay. For the benefit of those who are new, I'm just going to really quickly go through the course mechanics really quick. The textbook is this one here, and there's a reading assignment in that textbook for each day. And there's a reading quiz, and we'll talk about that in just a moment, how you find it. There's also a tutorial text, and this comes in 2 volumes. It costs $100, but the bookstore has arranged with the publisher to just print those worksheets that we need this semester, and they're selling it for $5.75. It used to be $4.50, but everything's going up. But still, that's cheaper than the $100 book, so I think that's a good deal. I'll show you where to find the reading assignment. There's 3 different places where you can find it, but I'd encourage you to read slowly and not just skim through it. The ideas are dense, and they take a while to wrestle with, and so don't rush yourself on that. During the COVID period, I put all of my lectures at Montana State University on YouTube, and you can find those at that URL. And this is what it looks like. And The Physics 105 class, they called it Physics 205. Everything's inflated in Montana. It's close to Canada. And so that would be where you'd go if you needed to review some of the Physics 105 concepts. And speaking of concepts, the advantage of this website is that I've taken each lecture and broken it up into 5-minute chunks, each one covering one particular topic. And so if you're confused about one idea, you just go and find that quick concept and watch the 5 minutes. Now, the Physics 106 class, we called it Physics 207 in Montana. And so these would be the lectures that you would, and these are just as a resource. You know, if you had to miss class and wanted to know what we covered, you could go back. And these lectures here are what we're going to cover before the first midterm. These lectures here, electric fields and forces and electric voltage, are what we would cover before the second midterm. Electric circuits are before the third midterm, and magnetism before the fourth. And just like in Physics 105, the final exam is really a fourth midterm. It just covers the new material, not an overview of everything. If it's not too much trouble, would it be so hard to just push that button? I don't get any money, but still, it'd be nice. Okay. Now, tutorials are meant to be in person. And when I was hired 2.5 years ago, I was promised, I was handed a whole bunch of money, and I was promised that I could use that money to renovate a big space and fill it with small tables, and that would be a dedicated place where we could do tutorials. And I was promised. And when I got here, what I found was that the physics department was suddenly involved in a building project where they put that brand new building on the north side of the science center. And suddenly my room was not the top priority. And so what they did instead was they scattered us all over campus in little tiny traditional rooms with traditional desks, and they put 30 students in a room. Some of you are from that era, and you remember we were crowded in there so tight we couldn't really hear ourselves think. And so it was not optimal, but we tried to make it work. There was some frustration. Last year, the first time I taught Physics 106, we were expecting 340 students. That's the traditional number, the historical average. And instead, we had 200 extra students on the waiting list. And so I opened up a new section of the lecture in the afternoon at 3:30 in the afternoon to get those students into 106. But we couldn't find the little rooms for the tutorials last minute. That wasn't possible. So what we did as a compromise is, instead of in-person tutorials, I recorded the tutorial as if I were a student. I made a video recording of me working through the worksheets question by question. And then the students would watch that video and then work the tutorial homework. Now, as far as morale went, it was great. There wasn't the frustration of the crammed in classrooms, but the learning wasn't as deep, I didn't think, as what it could have been, because you weren't actually doing it yourselves. So it was a compromise. Well, last semester in Physics 105, many of you were in that class. Again, we had 200 extra students, and we had to open up again another lecture section in the afternoon at 3:30. Again, we couldn't find rooms for the tutorials, so again, we did it online. Well, this semester, We have 560 students, which is 20 more than the 200 extra that we had last year. So you people are legion. You're just, how many of you are going to go to med school? Yeah, I hope you're right. Okay. You're accurate on that. But I think that's what's driving it is we've opened up this med school and suddenly we've got all these new students that are wanting to be doctors. So anyway, what I'm saying is I still don't have that promised room. They're telling me I'll get it by fall of this year. Okay, but this semester, we're just going to be doing it online, watching the video again, like you did in Physics 105 last semester. Again, it's a compromise. It's the best we can do. But in your schedule, your course schedule, there's 2 times associated with your section, but this is the only time you're actually coming to class, 12:30. Okay, ignore that other time. So questions on that? Anyone? Okay. Now, what is a tutorial? If it's running properly, it's where a group of 4 students work through some exercises that challenge their view of the universe, push them up against their misconceptions. The small group is it works best if we have 1 teacher for every 7 students. And so it would work best if we had 21 students in a room with 3 instructors. And those instructors were going around from group to group, conducting what we call a Socratic dialogue, asking you questions rather than giving you answers, asking just the right questions to help you discover the physics and put together the physics so that you own the physics from the ground up. It pushes you in a direction where you think you know the answers, you're sure you know the answers, and then pow, you up against the wall where suddenly your predictions don't come true. And only then are you humble enough to change your view of the world around you and rebuild your model of physics, okay? So that's the way it's supposed to work. Homework comes in 2 flavors. With each tutorial, there's a tutorial homework online at the MAC site, and those questions tend to be more conceptual. There's less number crunching in those questions, and they tend to be more similar to what you see on the midterms. And so that homework is a very good preparation for the midterms. It's due typically on Monday. There are a couple that are due later in the week, but always at midnight of the day they're due. And they're found at the MAC site. We'll talk about in a moment. The second homework is straight from the textbook. The end of chapter problems have been migrated over to MAX. And those problems, you do a whole lot more number crunching. And indeed, MAX, one of the main reasons for using MAX is that it can change the input numbers for each student. So even though you're all solving the same problem, you're not solving the same problem because you've got different numbers than your neighbor, okay? And that's due at midnight, either on Tuesday or Friday. So the homework that's associated with today's lecture will be due next Tuesday at midnight. Now, the reason for that is that if you get stuck, you know, if you have trouble with those problems, we can talk about that on Tuesday during lecture or before lecture. I will be here at noon every Tuesday and Thursday just to answer questions before class starts at 12:30. And so you've got a half hour to ask questions about the homework, questions about the tutorial, questions about the material in the book, anything at all, okay? Now let's talk about that MAC site. That's where you can find the lecture notes, the homework assignments, the solutions will be posted after the homework is due, and sample exams and their solutions will be posted. I'm going to wait until we're closer to the midterms before I post those. I don't want to scare you with those sample exams before you're ready. And then you can find your grades there. So this is what the Max, how many of you haven't used Max before? Any of you? Okay, a couple of you. You can get there from Learning Suite. It'll just jump you over here. But let me give you a feeling for what it looks like. On the main page, you've got the weeks and some announcements. And if you go up here and click on schedule, you get all of this, all the links that take you to your assignments. And for example, if I click on that homework number 1, the one that's due next Tuesday, it takes me right to homework number 1. Now, remember, each and every one of you are going to have different numbers. In this case, I have a spring that has been stretched by 21.1 centimeters. You might have 24 centimeters. Now, when you're done with the problem, you can hit the submit button. And you can hit the submit button as many times as you want, bank your points. But here's the danger. If the problem has multiple parts, A, B, C, and D, and you submit after B, well, it's going to give you credit for A and B, but then it's going to change all the input numbers. And so if C and D depend on your answers to A and B, you got to go back and rework A and B with the new numbers. So you want to wait until you're done with A, B, C, and D, and then hit the submit button. If you've been in Physics 105 with me, you've already known that. But the new people, please be aware. Questions on that? Yes. Yes, and that is an important thing to remember, is that for most of the problems that involve numbers, if you get it right the first time, you get 100% of the points. If you don't, you get to try a second time. And if you get it right the second time, you get 100% of the point. And if you have to take a third try, you get 80%, and the fourth try is 60%. Anyway, it works its way down. But with a multiple choice problem, you chose C and the answer was A. And Max comes back and says, I'm sorry, you chose wrong. The answer was A. Well, you don't get another chance because the answer is A, He just told you that. So you have to be careful with the multiple choice questions, that you're sure of your answer before you hit the submit button. Okay? So the class assignments, this is one place where you can find the reading assignment. That's a link, and it's got the reading assignment of chapter 12, section 1, and chapter 12, section 2, and that's due at midnight tonight, okay? And if you click on that link, it takes you to this reading quiz. And quiz is a strong word. It essentially just asks you, did you read, did you not read? And that's always going to be the case. Did you read or did you not read? And it's worth 5 points if you read. Okay. Now, the other place where you can get the reading assignment is right there. And right there. Okay. Now, how many of you don't have a main textbook yet? Okay. Do they have any in the bookstore? Does anyone know?
You can get it online.
What's that?
You can get it online.
You can get it online. Yep. There are plenty of opportunity to get it online. But I think last year the bookstore ran out. I haven't gone over to check this year. I posted chapter 12 at the PDF at the Mac site so that you have it if you're still waiting for your book to come in from your order. I can't post anything past that without violating copyright law. And so you need to worry about getting yourself that textbook as quickly as possible. Okay. If we go to that schedule page, we also have a place where you can go to the tutorial homework and complete that. And we also have a place where you can find out when to take the exams. Now, Again, how many of you took 105 longer ago than last semester? Okay, I got some news for you. I was teaching Physics 105 the way they told me to teach 105, and that is cram it all in, okay? And that's what they wanted. And so as a result, we found that we were testing on old material while we were lecturing on new material. And because the exams were open for 4 or 5 days, we found that a lot of people didn't want to learn the new material while they were still cramming for the old material. And so we found that it didn't work very well. Well, last spring, the academic vice president challenged us to do something to help our students succeed, find a way to help more of our students be successful. And what Dr. Benyon and I felt was that we're just rushing through this material way too fast, and we need to fix that. And so what I did is I took the material on waves and shoved it back into Physics 106. And so instead of having 5 midterms in 105, we just had 4. Okay? Now, I got in serious trouble for that. The department says, you can't do that. You can't do that. And my response was, what you gonna do? Want me to retire again? I can do that on Tuesday. So anyway, I got away with it because I'm a rascal. But the reason we wanted to have less material is that we wanted to do this experiment with exams. Each of our midterms now had an A form and a B form. And so what happens is you've got a couple of days to take the A test, and then after you take the A test, in class, in this case it would be Thursday, January 29th, all we're going to do is go over that exam, question by question, every detail of the answers in that exam. And then on the next day, you get to take a second exam over the same material, and you get to keep whichever grade was higher. Now, did this work in Physics 105? I think it did. What we found was that about 64% of the class got an A in the class. And that's much higher than any other class, physics class in the department. And I'm not ashamed of that, because that's what the academic vice president asked us to do. He said, don't dumb it down, don't water it down, but help them be successful. And what we found was that of the people that took both A and B exams, about 70% of the students did better on the second exam, improved their score on the second exam. And so I think that this is the way to go, and that's why we're going to keep doing it in Physics 106. Are there questions on that testing policy? Yes, sir.
Is that for every midterm?
It's for every midterm except for the final. The final by university policy has to be open for the entire final period. And so like Physics 105 last semester, that was a one-shot. But all of the midterms will have an A and a B part. Now you notice that when people ask questions, I come up to them. And a lot of you know why, but the people that haven't had me as a teacher don't. I'm deaf, okay? When I started this job, I went to an audiologist and they told me that I am only understanding about 25% of the words. My hearing has degraded a whole bunch this last year. So essentially I'm doing this. I was just in a meeting, a faculty meeting where I got nothing. I mean, so when you ask a question, don't be offended if I'm right in your face, okay? I got to see your lips move if I'm going to understand what you're asking me. My wife is constantly grabbing my chin and pulling me over. I like it when she grabs my chin. I'm not dead yet. So anyway, just be aware of the fact that, and when you're in my office, be patient with me. You know, if I keep saying what, just say it louder and slower. Okay, pretend I'm from another country. Okay, in the class notes section, right now there's also a section where it would say chapter 12, but when I took this picture, there was only today's lecture, simple harmonic motion. And if you click on that link, you get essentially a PDF of today's PowerPoint lecture. And so you really don't need to be frantically scribbling notes during lecture. You should be trying to incorporate the ideas and understand what's going on, because the lecture is going to be at the MAC site. Okay. We measure attendance to encourage attendance, and that's worth 5% of your course grade. And we measure that attendance with the clickers, and the Max software doesn't work with the online clicker system, with the phone clicker system. So you actually need a physical clicker. It could be a iClicker 2 or an iClicker Plus, or does anyone have an iClicker 1? These are the cheapest. They're like $5 on Marketplace or eBay. But you need to get one. Today, everyone's going to get a perfect 5 out of 5. Okay? But try to get one by next Tuesday so that you can get your points. Now, again, when you click, your points are associated with that clicker. And we don't give extra points for getting a right answer, just for giving an answer, being here. And if you don't register until the end of the semester, as soon as you register your clicker, all of those points that are connected to that clicker will come pouring down on your head like blessings from heaven. And so that works. But if you perchance lose that clicker before you register it, all of the points that are attached to that clicker are lost with it. And so I would encourage you to register your clicker today. You just as well. Okay. Your grade is the same as in Physics 105. Each of the midterms is worth 15% of your course grade. The final exam is just another midterm, so it's also worth 15% of the course grade. The tutorial homework, 15%. The participation clicker points are 5%. The reading quiz is 5%. And the lecture homework is 15%, giving you 100%. These two categories are combined in the grade book under the category of class. Half of it's clicker and half of it's reading. Now, we dropped the lowest 5 participation scores in anticipation that you might be out of town at a conference. BYU's interesting. I've had so many emails about, I got married last weekend and I'm on my honeymoon. I won't be back till Wednesday. I never got those emails at Montana State University. It's just amazing. Yes. Enjoy Cancun. Okay. The grading scale is the same as in Physics 105. 90 and above is an A, 85% above is A minus, and the same as before. And as you found last semester, if you got an 89.5, I rounded up. Okay, I rounded up. Okay. Are there questions on the grading? Okay. Office hours, as I said, I will be here every Tuesday and Thursday at noon, a half hour before class starts, to answer any questions you have. And then on Monday, Wednesday, and Friday, from 9:30 to 11:30, I'll definitely be in my office waiting for you. But the important thing is, I'm here to teach. I was hired at the ripe old age of 67. I'm 70 now, and there's just my career ended when I left MSU. So I'm not here to do research. I'm not here to work with grad students. I'm here to teach. And so I've got twice as many classes as the normal professor in the physics department. But that's because I like what I'm doing. Teaching is my life. And so when you come with a question, you're doing me a favor. And so you can phone me, email me, text me. My cell phone number is in your syllabus, so you have that when you need me. So don't hesitate to come see me. Let's talk about what we'll learn in Physics 106. First off, we'll learn about waves. And those of you that took 105 a while back, that was what we studied in 105. And so you're going to be stuck learning it again. It'll be boring. I apologize. Take a nap, okay? But it'll be okay. Today we're just going to build the foundation of waves, and it's going to be fairly straightforward and boring. But next week we're going to talk about Doppler shift, beat frequencies, Mach cones, and then the week after that we're going to talk about music, standing waves, and organ pipes and guitar strings and things like that. So it gets much more exciting as we go along. And then we're going to talk about electric fields and forces. And the key word there is forces, okay? We're going to learn some ways of figuring out how big the electric field is. But once you figure out how big it is, it's a force. You put it on your free body diagram. You use Newton's second law, F net equals ma. So what you learned in that second part of Physics 105 is going to be extremely important in 106. Okay. Now, the third part of the class is electric circuit. And this is my favorite part. If I could just teach nothing but electric circuits all year round, that would be my dream job, And that's because when I learned electric circuits, I learned the traditional way, which was very mathematical. You set up a bunch of equations, simultaneous equations, and you grind through them. And then you get an answer that means nothing, okay? I went through that as an undergraduate. I went through that as a graduate student. I could solve any of these circuit problems. I had no idea what was going on in those circuits, okay? It wasn't until I went to work with Lillian McDermott, the author of your tutorials. I was part of her group when these tutorials were written. I was the first instructor to actually take them into the classroom and go back and report what needed to be fixed. Okay, so I'm really sold on these tutorials. But it was working through these tutorials, like you're going to be working through the tutorials, that I first understood what the circuit was doing. We actually we're going to build a model, a conceptual model of what's happening in those circuits. And this is going to be one of your homework problems. And I'm going to ask you, I'm going to say, if those 7 bulbs, flashlight bulbs, were made at the same factory by the same worker on the same day, his name is Sven, okay? They're identical bulbs. They're hooked to that one battery on the left. Which bulb's going to shine the brightest? Which is going to be the second brightest? Which is going to be the third brightest? And so forth. And you're going to be able to say, Greg, bulb number 1 is going to be brightest. Bulb number 7 is going to be second brightest. Bulb number 6 is going to be third. 2 and 3 going to be tied for next. And 4 and 5 will be tied for last. And more importantly, it's just going to make sense to you. It's going to be obvious. And you're going to be able to explain your reasoning, justify your answer. Okay? And that, I think, is a powerful tool. Now, after that, we're going to cover magnetic fields and forces. Now, you remember in Physics 105, we left rotational mechanics till later in the semester. And that's because we found some weirdness in rotational mechanics that made it challenging. We had several right-hand rules that we had to use to figure which direction that torque was going to point, because it always pointed perpendicular to the direction we thought it was going to point. Well, when we get to magnetic fields and forces, we're going to find the same thing, the same weirdness, okay? And we're going to find 3 right-hand rules that we're going to need to figure out the direction of that magnetic force. And that's why we're going to save it to the end of the semester. And I mean the end of the semester. That's it. Now, we used to cover optics and a little bit of modern physics in the end of 106. And there's not room. Not if we're going to go at a reasonable pace. And a lot of you are going to be taking the MCAT. And on the MCAT, there is optics and a little bit of modern physics. Now, at Montana State, we had a very high acceptance rate into medical school. 92% of our students that applied got into medical school. And they came back and reported that they did very well on the physics portion. Now, the way we made that happen is every spring I would offer some night classes free of charge where I just went over optics and I picked out those topics of modern physics that were typically on the MCAT. And it turns out that in a couple of nights we can cover those topics. They're not that challenging. I also have videos from last year's 106 class covering those topics in all their gory detail if you would like more than just a couple of evenings. But I'm happy to do that as you get ready for the MCAT to help out. Okay, are there questions on these topics? That you're going to be doctors, okay? I still need my appendix out. One of you is going to have to do that. Okay, one of the things we're going to do when we talk about magnetic fields and forces is magnetic induction, and we're going to understand this magnetic track here where we've got a superconducting puck. I paid $7,000 of your tuition dollars to get this from Israel, and we're going to play with it in class.
Oh.
Meet George Jetson. Okay, that's enough of that. Okay, let's talk about today's topic. Simple harmonic motion. And the key word there is simple. And I'm going to point out in a few slides here what the simple is in simple harmonic motion. Now, because this is the first day of class, we've got the reading assignment for today and the reading assignment for Tuesday. But typically, I'm just going to have the reading assignment for the next lecture. And that's always going to be on the front slide of the PowerPoint presentation. Okay, so that's the third place where you can find the reading assignment. I have here a spring hanging from a bar. And if I put a mass on that spring, it stretches the spring now down to a new equilibrium position. Okay, so I put on the mass and it stretches the spring by some amount to an equilibrium. Equilibrium means happy place, where it's just going to stay. If I don't disturb it, it's just going to stay there forever. Okay, the net force at that location is 0. Now, that stretch we call delta S. And for those of you that had waves in 105, this is boring, but it's okay. If I put half a kilogram on there, and I did, and it stretches the spring by 0.29 meters, and it didn't, this is the spring they gave me, the best one that I could find in there. So anyway, let's make believe that it's stretched by 0.29 meters. What's the spring constant of the spring? With your neighbor, figure that out. What's the spring constant of the spring?
Last semester. That's great fun.
Yeah, okay, correct.
Okay. Some of you have been done for a while and some of you are quite a ways from being done. That's okay. Okay, let's do it together. I hope you remember Hooke's law after Robert Hooke. And essentially it just relates the force exerted by the spring to the stretch of the spring. Okay, the force exerted by the spring, and this is the stretch of the spring, and this is the proportionality constant, is the spring constant. Now, remember, in physics, we've got so many minus signs, and they tend to trip us up. They tend to be the part that gets us in trouble. And so the more minus signs we can get rid of, the better off we are as human beings. And so this is one that we need to just get rid of. All it's saying is that if I stretch the spring down, it pulls up. I knew that, okay? So let's just dispense with that minus sign there. And so if I just look at Hooke's law without the minus sign, and I do a free body diagram, a half of a kilogram, if we were on a planet where the gravitational field strength was 10 newtons for each kilogram, that would weigh 5 newtons. Well, on our planet, it's actually 9.8 newtons for each kilogram, so that would be 4.9 newtons. As you remember from Physics 105, we typically do our questions in the homework and on the exams on that really magical planet where the gravitational field strength is 10.0. At Animal Kingdom, I went on the Avatar ride. It was a different planet, and it was amazing. It was amazing. It was amazing. Okay. Okay. Now, since that block is not accelerating, that means that the force by the spring on the block, has to be 4.9 newtons. If the stretch were 0.29 meters, I could just do a simple division and get a spring constant of 16.9. We pronounce this newtons for each meter. And that's the gut level understanding of what a spring constant is. How hard I would have to pull to stretch that spring 1 whole meter. Now, clearly, if I stretch this spring 1 whole meter, I bought it. It's never going back in the box. It's broken, okay? And so you have to be a little bit clever. You know, how hard do I have to pull to make it stretch by 1 centimeter and then multiply by 100, something like that, okay? Now, that, my friends, that was Physics 105. That was review. That's not what we're doing in Physics 106. That's Physics 106. And we call it simple harmonic motion. Simple harmonic motion. Okay, up and down, mass on a spring. Now we can characterize that motion by the timing, and we can do that 2 ways. We can either talk about the period of the motion, that's how many seconds it takes to make 1 whole complete cycle. one down and back. So it gets back to its starting place, okay? Or we can talk about the frequency of the motion. How many times does it do a complete cycle in 1 unit of time, 1 second, 1 second, okay? We can also characterize this simple harmonic motion by the amplitude of the motion, and we define the amplitude as the maximum distance that it gets away from its equilibrium position, its happy place. And we characterize that, or we denote that rather, with the capital letter A. But A is just representing some number. If the amplitude happens to be half a meter, then A is half a meter, okay? Just by show of hands, how many of you deeply care about this situation of a mass bobbing up and down on a string? This is the problem that you came to BYU to figure out, to learn how to solve. How many of you? Really? No, no. I don't think so. You notice my hand's not up either, okay? It just doesn't seem that exciting. So why are we spending time on it? And the answer is, if you had special glasses that could see microscopically, what you would see is that everything that appears solid is really made up of little molecules and atoms that look a whole lot like this mass. And they're connected in a lattice work where they are connected to their neighbors with electrical forces that look a whole lot like springs. And so if we could see microscopically, the world around us would look like a bunch of masses connected to each other by a bunch of springs. And so if we can understand this problem, we can understand a whole lot of the world around us. It's huge. Now, I did not fully appreciate that as an undergraduate at BYU, okay? I went through all of my classes. I learned about the silly mass on a spring, but I just thought it was that, silly. When I went to graduate school at MIT, I found that MIT brings graduate students from all over the world. All the geekiest grad students come to MIT. And they're not sure what the grading scale means in their country. And so the first thing they do when you arrive on the bus is they put you in a 5-hour exam called the qualifying exam to see whether you can stay, whether you're good enough to stay or whether you got to get back on the bus. Now, I knew in my heart of hearts that I was not good enough, that I was not going to be able to pass this qualifying exam, that I was going to have to get back on the bus. And when I opened that exam, the first question on the exam showed me that I was right. In that exam, the first question was a big old motor that was turning in a circle. And it was sitting on a thick pad of rubber. And they wanted to know what rotational frequency would you have to have this thing rotating at to get the maximum jiggle on that rubber mat. 4 years at BYU, I'd never seen anything remotely like that problem. I had no idea how to solve that problem. And I was just sitting there looking at that page, trying to figure out how I was going to tell my wife that we had to pack everything up again and go home. Okay? And then suddenly I realized that the heavy motor was just a mass. And the thick rubber mat was just springy, like a spring. And they had given me enough information that I could figure out the spring constant of that spring. And suddenly it was just a simple Hooke's law problem. And I solved that and turned the page. And wouldn't you know it, the good Lord blessed me with a second mass on a spring problem. That problem is what got me to stay at MIT, which got me this job, which got me the opportunity to work with you. That may not mean much to you, but it means the world to me, okay? And we're going to study it. Now, let's just go over some basic facts. A block on a spring bounces up and down every 0.25 seconds. How many times does it bounce up and down in 1 second? Shout it out. 4. It's that easy. If you know the period, you know the frequency. Okay, in this case, the period, how long it takes to make a cycle is 0.25 seconds, always in seconds. The frequency is just 1 over that, or 4 times per second. And we pronounce that hertz, okay, to honor a dead physics professor. Not a bad thing to do with your life, okay? So if you know what the period is, you could take 1 over that to find the frequency. If you know what the frequency is, you can go 1 over that to find the period. If you know one, you know both. That makes sense? Check on your neighbor real quick.
Got that? Good? Yeah. I don't say, jump.
Okay. Let's see how we do. This is an old exam question. What is the frequency of the second hand on a clock? This is an analog clock, not a digital clock. I'm going to get you started with your clickers.
Yeah, so number of cycles.
Okay, now you can click. And I hope you remember, you can click as many times as you want. It always saves your last answer. And if you're not sure that it registered your click, just click again. It only measures 1 click per student. Okay?
What's insane?
And I hope that you all have your iClicker set to the frequency AA, because that's the default frequency, and that's the frequency that this receiver uses. If you have it set on something else, you're not getting your points.
Oh, like, oh, the. Even I click for bio now. I was like, oftentimes once.
Okay, last call. Again, everyone's going to get full credit for attendance today, 5 out of 5.
It's just.
Good, the answer is D. Frequency is just the number of cycles divided by the number of seconds. And a second hand goes once around back to its starting place in 60 seconds, 1 minute. Okay, and so that gives me a frequency of 1/60th of a hertz. 1/60 of a hertz is the answer. Okay. Now, suppose I wanted to use the same spring, but I've got a whole bunch of different masses. Would I want to increase or decrease the mass to increase the period of oscillation? That's what it looks like with a 1/2 kilogram. Would I want to go up to a full kilogram, or would I want to go down to 200 grams? Talk to your neighbor real quick. What would I want to do?
Make it more.
Okay. First of all, we need to ask ourselves, what's that going to look like to increase the period? Well, if I increase the time it takes to make 1 cycle, I'm slowing things down. And slowing things down happens when I've got more mass. Mass is how hard it is to speed something up or slow it down. And so if I increase the mass, that is going to, let's do it that way. That's going to slow it down and take longer to make 1 oscillation. If I want to increase the frequency, that would be decreasing the period. I would go to this. Come on, Greg, you're better than that. Okay, so In this case, I'd use a smaller mass. Boing, 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 okay? Okay. Now, let's talk about amplitude. In addition to this mass on a spring going up and down, there's another flavor. And this flavor is much easier to work with. And this will be the type of flavor that we're going to use more often than not. And that's where the spring is attached to a block and the block goes back and forth horizontally on a frictionless surface, a frictionless table. Okay. Now we can work this problem with friction. It's a wonderful problem, and we work it in the upper division physics classes, spend a lot of time on it. But trust me, we do not want to go there in 106. So we are always going to use a frictionless surface in this class, okay? But this thing goes boing, 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 boing. When it's over here, the spring is compressed. When it's over here, the spring is stretched. And these, I pointed out, are the turnaround points where it changes direction and goes the other way. So the question is, what is the amplitude of that motion? With your clicker again, I'll get you started. Now you can click.
You said 2 was at 8.
Hey, if you turn it off and turn it on.
So, I'm sitting.
You're good. Not everyone. It could be now.
These are 2 pin.
Nice. Well, that stretch.
It like
Yeah.
back.
Right. So,
Yeah, I got it.
have you started that yet? I'm getting all
Okay, so
I trust there's so many.
Okay, last call. Get your vote in.
just like really dizzy. Getting her back.
Okay. We're not as sure this time. We're not as sure. The answer is A. A. And that's because of our definition of amplitude. Amplitude, remember, is the maximum distance it gets away from where? Equilibrium. So first of all, we have to find out where equilibrium is. Okay? So equilibrium is where the net force is 0. Well, over to the left, the spring is pushing, it's compressed. Over to the right, the spring is pulling, it's stretched. Right in the middle is where the spring is exactly the same length as it was when it came out of the box from the factory. That's the happy point, the place where it would stay forever if you didn't bother it. It would just be happy right there. Now, it travels away from that equilibrium point by 2.25 meters or 25 centimeters. And so that is the amplitude by definition, Yes, sir.
Is there a situation in which the equilibrium would not be exactly in the middle?
What did he say?
I was asking if there's ever a situation where the equilibrium is not right in the middle.
Oh, no. And when I say no, what I really mean is heck no. Okay. So here's another question. I've got a block hanging from a spring. It's pulled down 10 centimeters and released. It bounces up and down at a rate of 3 times every second, or 3 hertz. How could this rate be increased? How could I make it go faster? These are your options, or you can suggest another one. So with your neighbor, which of these, or maybe another one, would make this frequency increase? Talk to your neighbor.
Or is it like one of these? I was doing it hanging.
The strings. I think that was it.
Yeah, I think this is the thing I got used to with. It doesn't matter how much. Put down on. So I don't think pulling it down doesn't make period.
My 1 kilogram. Okay, brave soul, raise your hand and share. What did you come up with, brave soul? Don't be cowardly. Oh, there we go. Remind me of your name. Preston. What do you got for me?
Decrease the mass. Stiffer.
Okay. Decrease the mass and make the spring stiffer. What else? Anybody?
Don't pull it down as far.
Don't pull it down as far. Okay. What else? I've got great news, people. I have great news. It seems to me that pulling it down not as far should make it go faster. It seems to me that getting it started faster should make it go faster. There's lots of things that seem that they should matter. But the universe doesn't work that way, thankfully. It turns out that these are the only things that matter when it comes to the timing. Let me show you that. If I pull it down a little bit, I get 1, 2, 3, 4, 5, 6. If I pull it down a lot, I get 1, 2, 3, 4, 5, 6. If I pull it down really quickly, 1, 2, 3, 4, 5, 6. If I pull it down slowly, 1, 2, 3. You get the idea? It just don't matter. It just don't matter. And that's our main point for today. This is the simple in simple harmonic motion. And that is, it only depends on 2 things. It depends on the stiffness of the spring. That's the restoring force. Okay. And it depends on the inertia, how hard it is to get something to start or stop. What happens is, as I pull this away from equilibrium, the restoring force is always trying to get it back to equilibrium. Okay. But once it gets to equilibrium, the inertia makes it overshoot, keeps it going. It can't stop instantly. And so then it goes past, and suddenly the spring is out of equilibrium again. And so then the restoring force comes back into play. Now the key is that the timing never, I mean never, depends on the amplitude. Now in the homework problems, we're going to give you the amplitude. We're going to give it to you. But you shouldn't use it. So if you don't need to use it, why do we give it to you? And that's because I'm evil, okay? Because you're going to be doctors, and as doctors, you're going to have a whole bunch of data that comes in on you, and you got to figure out what's important and what's not important. What's going to make this patient live and what doesn't matter. And the same thing's true with these problems. If you're talking about timing, amplitude never matters. Never matters. That's a simple in simple harmonic motion. What we find if we solve an ordinary differential equation, which is beyond the scope of this course, is that the period of oscillation depends on the mass and the spring constant in this manner: 2 pi times the square root of the mass over the spring constant. Now, because the frequency is 1 over the period, I just flip this upside down and I get a formula for the frequency. Now, these two formula will be on the front page of your midterm. You won't need to have those memorized, but they are very useful. And again, I wish I could drag you through all the mathematics where we get that from, but it's something that is not a prerequisite for this class. Okay. Now, this formula gives us a second way to find the spring constant. You remember our first method, we call it the static method, was just to take a mass and hang it on that spring to a new happy place and just measure the stretch and use Hooke's law. Well, the second way is I bounce it and I use my watch to measure the period. And if I know what the period is, and I know what the mass is, I can find the spring constant, right? This has been a disaster. Okay, so let's say I've got half a kilogram and it takes 11 seconds for it to go up and down 10 times. That means my time, my period, is 1.1 seconds. Well, I could solve for the spring constant by solving this equation for K. Because it's under that radical, I need to square both sides. And then I get K over here by cross multiplying. I get it out of the basement by cross multiplying, bring the T squared down, the K up. And that's my formula for K. I plug in the mass, I plug in the period, and I get a value. And I'll get the same answer either method I use. Now, this is a useful fact that engineers use. Pi squared is really, really close to 10. And so when you're working your problems, you could just say, oh, that's 4 times 10 times the mass. In this case, the mass was going to be half a kilogram. So 4 times 10 is 40. Half of that is 20. Divide that by 1.1 squared, and you got your spring constant. Okay? Check on your neighbor. Do a buddy check real quick. Okay. We have 5 minutes left, and I want to use that 5 minutes to help you with the first homework problem that's due on Tuesday. Actually, before we do that, this is just really quick. A 2 kilogram block hangs from a spring and oscillates with a period of 1 second. What massive block come from the same spring would have a period of 2 seconds? Well, I'm just going to rush you through that. If I want to double the left-hand side of that equation from 1 second to 2 seconds, I've got to double the right-hand side. If I double the mass, that's not going to do it because it's under that square root symbol. I've got to multiply the mass by 4 in order to make the right-hand side of this equation bigger by a factor of 2. And so I'm going to have to use 8 kilograms instead of 2 kilograms. That makes sense? Yes, sir.
If you had already squared, get rid of the square root, could you just multiply it by 2?
If I squared both sides, I have to square that. And then doubling the t is going to make this side 4 times bigger. Yeah. Yeah, math keeps working. That's the beauty of it. Now, the first homework problem is asking you about, well, when is the acceleration 0? When is the velocity 0? When is the acceleration maximum? When is the velocity maximum? And so let's talk about that in the simple case of the horizontal mass on a spring, back and forth, left and right. That's the amplitude, the furthest it gets away from equilibrium. The net force is 0 at the equilibrium point in the center, always the center, okay? Now, the net force over here, if I draw a free body diagram, I've got the weight down, I've got the table pushing up, and the spring is compressed, so it's pushing back towards equilibrium. And it turns out that that spring force is given by Hooke's law, and it's Ka. Now, wait a minute, Greg. You said that Hooke's law was K is equal to, or F is equal to K times delta S. Well, it is, where delta S is the spring stretch or compression. But when you're at the turning point, the turnaround point, that delta S is equal to the amplitude, capital A. And so delta S and A are the same thing, okay, at that point. And so I can write that as K times A. And it's to the right. Now, if I look over here, again, a free body diagram is going to give me a spring force to the left because now the spring is stretched, but it'll again be K times A. Now, where does A equal 0? Where the net force is equal to 0 by Newton's second law. So A is equal to 0 right here. But if you think about it, that's where the speed, the velocity is the greatest, okay? Because it's speeding up all the way to there, and then it's slowing down all the way to there. And then coming back, it's speeding up all the way to there and slowing down all the way to there. So this is where it's going the fastest, but the acceleration is 0. If we look at where the acceleration is the maximum, it's where the velocity is 0. Because that's where the net force is maximum. And the net force is what causes the acceleration. So whenever one of those is 0, the other one is at its max. Whenever one is at its max, the other one is at 0. A and V trade off of each other like that. Check on your neighbor. That's the answer to problem 1.
When you want to get to the end and then it comes back up, it speeds up until it gets a little point.
Okay. We have 2 minutes, and I'm just going to use that to introduce you to the other flavor, the vertical flavor, really quick. If I put a mass on that vertical spring, it stretches down to a new equilibrium point. If I pull it an extra distance A, the amplitude, it'll bounce back and forth, up and down between these turnaround points. The equilibrium point is right in the middle. That's where the net force is 0. And if I draw a free body diagram at that point, the spring is stretched. The force by the spring is not 0, but it's balancing the weight. Whereas if I look up here, the weight's still the same, but now the spring's not as stretched. So now I've got a net force down towards the equilibrium. If I look down here, I've got the same weight, but now the spring is really stretched, so I have a net force up. I'm using F net equals MA in both of these situations. Because the horizontal case is simpler, that's the case we're going to use on the exam and most of the homework problems. Okay, we're out of time. Have a great weekend, people. Thanks for coming back.
You too.